Okay, so we had some exciting formulas in the previous video, so take a look at that. So anyways, part 284C3M1B7C8E13C9C6C2. This is line 22f1fa19C3M1B7C8E13C9C6C2. Tetrahedron Crystal Miller Matrix Core UFO 5G Wow Seti. There's the alien radio signal. This one's about the cube, the core, the matrix, and the UFO structure designs. Euclid elements with ideas from, I don't know how to say his name, Msheiksirajuddeen, Alien Technology Wow Seti. So I found a blogger that talks about alien stuff, okay? So January 9th, 2013, today's the 13th. Keyword Euclid Tetrahedron 2 is from a previous video. This is the one you want to watch. It's got some really cool formula ideas in it. Line 22f1fa19C3M1b7C8E13C9C6C1. Zirconium atom Icosahedral formula UFO 5G Wow Seti. Actually, I should add the word core in there, but that's okay. Quotes, diagrams from the blog. Okay, so this is the shape you're going to be using with your tetrahedron. These are the math equations for it. Okay, this is the cube for the core, and this will be the circle that goes inside the core. And I'm running out of battery power already. So quotes and diagrams. This is representation of space, lattice, and unit cell. The representation of dimensions of a unit cell. Quote diagrams from blog. Crystal structure. I'll probably be editing this video, so I'm going to put 2 lines, 2 videos. Okay, so crystal structure. In crystal there is a systematic periodic arrangement of, so this is Msheiksirajuddeen.blogspot.com. He's got some really good ideas, so I found it on his blog. It's a quote from his blog, okay? Crystal structure. In crystal there is systematic periodic arrangement of atoms in all the 3 directions. Crystal has regular shape and sharp melting point. Crystals possess directional properties and hence called an anisotropic substances. Examples of crystals are copper, silver. I ran out of battery power again. So part 284C3M1B7C8E13C9C6C2, line 22f1fa19C3M1B7C8E13C9C6C2. Tetrahedron Crystal Miller Matrix Core UFO 5G Wow Seti. This is part of the formula that was in the last one. This is what it looks like, and let's pop down to where we stopped. So we're talking about the crystal structure, and this blogger is talking about what you can do with a crystal structure, which I didn't know all this stuff. He's saying there's crystals with copper, silver, and aluminum, which is cool because we're going to be using crystals with our design for the core. This is talking about the space lattice, an infinite array of points repeated in 3-dimensional space such that every point has surroundings identical to every other point in the array is called space lattice. And that's from Mohamed Msheiksirajuddeen, that's his name. So this is a diagram that he had on his blog here. This is a unit cell. The smallest part of a crystal is called a unit cell. It is formed by a combination of atoms and molecules. The whole crystal structure can be formed by the repetition of these unit cells. So it's A, B, and A sites. Now see the shapes? We have a triangle, which is the tetrahedron, and then we've got this hexagonal type shape, which is what we're looking for to use with our design for the engine. This is a close packed direction. So I don't know if we can use these math equations for what you want to make, but I'm wondering if you can mix your superalloys in with the crystals and then design the structure, melt it all together, and then have it form the shapes that you want. I'm beginning to think that's what we got to do. So this is, he's got all the math equations on how to do this body-centered cubic structure. So that's why I grabbed it. It's quite defined. And see how we've got this core in the area here, and we got 1, 2, 3, 4, 5, 6, 7, 8 things, but we're supposed to have a quadrupole, 6 quadrupole magnets, but we're also supposed to have monopole. So maybe we have 6 quadrupoles and 2 monopoles. Who knows? That's what I'm thinking here anyways. We'll find out, right? So this close packed directions, he's got all these calculations here. APF for a simple cubic structure. There's the Miller indices. So we got the triangle, which is our tetrahedron within the cubic matrix. So you're going to find the intercepts made by plane on the crystallographic axis. Express intercepts in terminal of axial units of unit to cell dimensions. Take the reciprocals of the intercepts. Reduce them to smallest integer by multiplying with their LCM and write them in parentheses. So whatever research work he's done, it needs to be used with the design of this structure. Important features of Miller indices. For any plane parallel to any axis, the intercept is made at infinity and corresponding Miller index is 0. All parallel equidistant planes have same Miller indices. If a plane passes through origin, then the Miller indices are found by taking a parallel plane having no non-zero intercepts. If a plane cuts the negative axis, then a bar is put on the Miller index. If a normal is drawn to a plane, then it represents the direction of the plane. That's from Mohamed, Msheiksirajuddeen.blogspot.ca. Got some really cool stuff on his blog. He's got other things there. He had tons of stuff. But this is what stood out because it looked like the core design, so I grabbed it. So this keyword from the data is going to be Compton effect, and I'm going to study that in our next set of videos. Actually, there's quite a few more videos coming up. Thanks for watching.